Hi everyone, in this video I would like to introduce our CVPR paper. It is called Lion. In this work will focus on point cloud generations. Our code is now open source and you can check out more visualization on the project page. In this work, we propose the SeaLion model which can generate 3D point clouds from Gaussian noise. And what is special is that the generated point cloud come with semantic segmentation labels. These generated label point clouds can be used for synthetic data augmentations, meaning that they can help to enlarge the training set and improve the performance of the segmentation models. On the other hand, SeaLion can also be used as a part of well 3D editing tool. Here we show example where the engine is fixed and SeaLion regenerate the rest part of the point cloud accordingly. Overall, SeaLion followed the general architecture of the Lion model from NVIDIA. It transformed the original point cloud to the global and local features and adopt a latent diffusion framework. Our main improvement in the architecture lie in two areas. First, we incorporate segmentation information as conditional input to both the point level encoder and decoder. Second, we upgrade the point level diffusion models so that it can generate not only the latent features H0, but also the corresponding segmentation. During inference, SeaLion global diffusion model first generate global features Z0, then the point level diffusion models produce point level features H0 along with the corresponding segmentation label Y. Finally, condition on both Z0 and Y, the decoder transform the latent features H0 to the final point cloud X. What is interesting here is the point level diffusion models. This module consists one down sampling data pass and two parallel up sampling data pass. The first data pass is used for noise prediction for the generated purpose. And the second data pass is used for semantic predictions. So the downsampling pass here is used to learn the common features, which are the yellow colored features here, while the two upsampling data pass separately learn the features for the noise prediction and the segmentation predictions. Another contribution of this work is the evaluation matrix. The common matrix used in point cloud generation tasks are mainly the 1NNA coverage and the minimum matching distance. This matrix essentially measure the distributional similarity between the generated set and the real set. On the final level, this require measuring the pairwise distance between two point clouds. Well, the most important metrics here is the chamfer distance. However, the existing discussion mainly focus on the generation of the unlabeled point clouds, but not too much work discussed about the generation of labeled point clouds. If we focus on these topics, then it becomes necessary to focus on both geometry quality, but also the consistency between the segmentation label and the geometry. This aspect remain unexplored in literature, mainly due to the limited number of the work focused on the generation of label point clouds. To the best of our knowledge, Defector is the only existing work that consider this aspect. In the following, we briefly review how Defector conducts such evaluations and discuss the limitation in its approach. Here we take MMD as an example because it is more intuitive than the 1NNA and coverage. The evaluation here involve two for loop structure. The first loop, meaning the outer loop, iterate over the individual semantic paths like the car body, the wheels. And for the inner loop, which is the second loop, it iterate over the generated set in GP, and it compute the distance between the parts in the generated samples and the corresponding part in the real samples. Here we take the car body as an example. For each generated samples, we compute the chamfer distance between its body part and all the corresponding body part in the real set. The minimum distance among the result serve as the MND value for the body part of the generated sample one. And this process is repeated for each generated sample to obtain the part level MND values across the generated set. The final MND score for the car body part is then computed as the average result over all the generated samples. And the same procedure is applied to other semantic part as well. Finally, the overall MND score is obtained by averaging the MND values computed for these four semantic parts. However, this evaluation method has a key limitation. It computes each part independently and fail to account for the coherence between different parts within the same sample. To illustrate this limitation, let's say now we have a real data set consisting of some labeled car point clouds, and we take some parts from this real point clouds and randomly put them together. You can see that the result is completely unrealistic. For instance, like this F1 racing car shouldn't have such a big and flat roof, but here this we have these weird combinations. However, if we use this synthetic set as the generated set for evaluations, then the MMD's score would be 0. This is because each part in the generated set can find exactly the same part from the real data set, and this leading to a 0 MMD. But despite the perfect MMD scores, it is very obvious that these generated samples are totally unrealistic and make no sense. So how can this issue be addressed? The core problem here lies in the order of the two for loops in the evaluations, and we propose to reverse the order of these two for loop, which can eliminate this inconsistency. To illustrate this, we analyze the same example again on this car point cloud dataset. Now for each generated samples, the distance to a real sample is computed by jointly consider all the semantic paths. For example, for this generated sample one, we calculate the distance for 4 paths between it and real samples. Then we aggregate the result by averaging or sum up all the results. The real samples with minimum average distance to the generated sample is identified, and then this minimum value is taken as the MMD score for the generated sample one. A low MMD value here indicates two important information. Assuming the generated sample one has the smallest distance to the real sample one. This means that each semantic part of the generated sample one looks very similar to the corresponding semantic parts from the real sample ones. And moreover, it also implies that all the semantic parts from the generated sample one, they combine in a similar way as the semantic parts in the real sample ones. So this means that this generated sample ones has not only very good geometry quality, but also has good interpart coherence. We refer the calculation within this highlighted bounding box as the part-aware chamfer distance. By repeating the same calculation for each generated samples, we obtain the MMD values for all the generated samples. And finally, we average all this result over the generated samples to obtain the overall MMD for the entire generated set. The part-aware chamfer distance methods can also be applied to one LNA and coverage matrix. So we not only evaluate the geometry quality of each semantic part, but also the interpart coherence. Now we come to the experiment result. Here we not only only show the NNA result, and more experimental result can be found in the paper. There are three baseline in this table. The third row is the previous mentioned defector, while the first two rows use a two-step methods to generate the label point cloud. That is, we first generate a label point cloud with SeaLion, the SOTA point cloud generation model, and then we apply the pre-trained segmentation models like PointNet, and Spottier for the segmentation predictions. You can see that SeaLion outperform all the baselines and get the state-of-the-art result across all these three ShapeNet categories. Here are some visualization of the generated point cloud. We only show the generated point clouds from three categories of ShapeNet, and more results can be found on our project page. Here is an interesting experimental result by editing the generated point cloud from SeaLion into the training set. The prediction accuracy of the segmentation model Spottier can be improved. Here is an example demonstrating SeaLion's capability as a part-aware 3D editing tool. Here, the gray parts denotes the frozen parts, while the remaining parts undergo a shape regeneration through a process of editing and removing noise. And this function can be further extended to like text-guided editing in the futures. Thank you for your interest in our work. We also welcome you to use our code for further exploration.